I have 10 o'clock, so we are going to get started this morning. So good morning, everyone. Good Thursday morning, a little bit warmer than last week, so that's good news, I guess, for most folks. We have our next Eastern Region Science Sharing webinar this morning, and it's going to be focused on discussing New York street flooding through a negative regression model and talking about impacts, challenges, for forecasting and anticipating major flooding events using various machine learning and algorithm guidance that Candace will be speaking about this morning. Candace Agonafir of Columbia University, supported by Dave Radell. I'm going to briefly introduce our folks this morning, but before I do so, just a couple of housekeeping reminders. This webinar is being recorded and will be uploaded to the Eastern Region Science Sharing webinar page after the recording. If you have any questions along the way, feel free to throw them in chat, or you can raise your hand at the conclusion of the presentation, and then we can field them from there. So with that, I'm going to introduce our folks. First off, pleased to have, again, Candace Agonafir. She has a PhD in civil engineering from the City College of New York, received her master's in industrial engineering from New York University, and a bachelor's in physical science from St. John's University. Some of her past research has involved utilizing regression and machine learning methodologies to provide useful information towards advancements in urban flooding detection, prediction, and prevention. Presently, she's a postdoc at Columbia University, where her research involves employing deep learning, specifically graphing neural networks, and to generate predictions on stream flow at seasonal and longer timescales. Her ultimate goals, by using continuous adoption of improved and newer machine learning techniques, she's hoping to become a impactful contributor within the field of civil engineering water resources via AI applications. And then we also have Dave Radell, the SOO, Science and Operations Officer at the WFO office in Upton, New York. He, of course, serves as the Research and Science Training Officer for the Forecast Office, helping to integrate new research data techniques into the forecast and warning operations process. He also leads the student program at the office, working with both undergrads and grad students from across the New York area to understand the challenges of operational weather forecasting. And he's very involved with probabilistic methods, forecast verification, satellite meteorology, and integration of valuable techniques into the DSS program locally. So thank you both for being here this morning, to Dave and to Candace. And with that, I will hand the floor over to both of you. Thank you again, and welcome to this morning's Eastern Region Science Sharing webinar.
Okay, thanks, Jordan. Candace and I are going to tag team this. We haven't practiced, so this will be fun. I'm really excited about this presentation this morning. And let me start by sharing the screen, and we'll kind of go from there, and give you a little bit of background about how we got to this point, and some of the challenges that we faced, and some of the kind of new science and technology approaches that we're using to try to address some of the challenges we have here, dealing with an environment that is highly urbanized. And so, Jordan, you can hear me okay? Just to make sure before I...
We are good to go.
Very good. So, nothing really surprising on this slide. Kind of the urban challenge for excessive rainfall. You look at our different numbers from last year, they're really not that different than what we've had in the past. Our CWA is pretty urbanized. I-95 corridor, New York City, even into parts of Long Island and up across the Hudson. Everything seems to be fast responding, whether it's a river or the ground. So it continues to be a warning challenge for us. You can see there we have a pretty good, last year, a pretty good POD and a pretty nice FAR. But our lead time has consistently been below the GIPRA. And so that's one of the things that we've tried to work on and tried to look at new techniques and new tools to try to help us get a little more lead time on our flash flooding. And so, it continues to be a warning challenge for us. And we've, over the last few years, have put resources into helping to try to improve that. Convective initiation of flash flood in an urban environment can be much less than the 60-minute lead time, 65-minute lead time that you have there. We've seen examples of that. And we also know that we could probably increase our lead time at the expense of the false alarm rate. And, is that really what we want? And that's one thing that we've discussed here at the office, and being a little more aggressive with our flash flood warnings, especially now in the IBW era where, you are unweeded when you have the baseline flash flood event. So some things that we've sort of batted around, and really, you kind of look at the numbers over the last few years. It's actually that last bullet, the zero lead time events. And so if we can somehow get some positive lead time on the events that we have zeros for, I think that'll go a little bit of ways in helping us improve that lead time. So, the urban challenge, some things that we've been talking about internally here, and again, trying to utilize some new tools and research to help us get that. I think, our warning paradigm here is probably not that much different than what others do, in terms of some of the newer tools that we're using. We do certainly make use of MRMS, and the hydrophobic is a worst case. It tends to overpredict for us in the urban areas, spatially and in time. Things that are maybe a little bit older, like the flash flood potential index, is not much use over the city where everything is just urban. And so, you have some limitation there. We have made some use, the good work out of the Buffalo office from last year or the year before, kind of looking at some of those instantaneous dual pole rainfall rates and trying to calibrate some of when that begins to show up at the ground, so to speak. We had a summer student a couple of years back, Joe Bauco, who is now at the State College office, who took a look, and you can see kind of at the right up here, kind of reworking based on the last 5 or 6 years of events, looking back through MRMS for the flash flood events we had, and kind of reworking some things in terms of decision thresholds for both urban and non-urban environments to try to give us a little bit of a heads up on some of those thresholds where you might start to really consider warning for urban areas just based on the values coming out of MRMS. So, we've tried to do some things to help improve those numbers. At the end of the day, I think some of the things, and this came out of IDA, the remnants of IDA, for sure, is that, the rainfall rate forecasting really is kind of the key here. We do have some pretty good, some okay to pretty good guidance now. But there's some additional, especially in the 1 to 3 hour time frame, coming out of some of the short-term or the CAM ensembles that we could certainly use. So we've made some use, at least looking ahead in that 3 inches in 3 hours from the HREF to give sort of a heads up. But again, that's certainly before warning time frame. All right. Whoa, this mouse. Okay. So again, just to kind of give a little more background information, the impact and visualization tools, especially when you're talking these higher end events, confidently messaging, especially in the urban environment where things are very fast responding, and you get the same rainfall amounts, you could have certainly vastly different responses depending on the rainfall rates, or obviously the axis of heaviest rainfall, which we saw during certainly during IDA. The key here really is in that second bullet for the city. Once you start exceeding that 1.25 to 1.5 inches per hour is really when you start to see trouble. And that 1.25 to 1.5 inch an hour rainfall rate, starts to overwhelm the drainage systems and the subways. And so, in a warming environment where we expect to see more of these kind of upper end rainfall rate events, this is becoming even more and more problematic. One of the interesting things to think about as we go on in time here is the idea of this impact-based modeling. And so it's certainly about, the weather piece, the hydrologic piece, if you will, and the weather piece, but I'm also trying to take a look at the impact of it too, as we kind of, as an agency, are in the DSS world, and thinking about impacts to lives and impacts to everybody, basically. you get to these, LSR for a road closure and that sort of thing versus kind of inconvenience. So as we've gone into DSS and we've gone into the sort of impact-based warning paradigm, yields an idea or maybe a more of an emphasis, if you will, on looking at some statistical modeling based on real impacts that are being noted here. So this is where our relationship with NOAA CESART, which some of you may remember NOAA CREST, which is housed at City University of New York, is a NOAA partner and a group there that does a lot of different things related to hydrology. So in some of our conversations with them, we determined that there may be some work that was being done there that could help us, at least in the cityscape, shed some light on some of these issues. And this is where where Candace enters the scene. Last year, even though our relationship with her and some of her work started really in 2021, Candace was part of a NERTO experience, a NERTO opportunity, which is run through NOAA's Office of Education. And it is aimed toward graduate students. So these are master's and PhD level students that are engaged in a project that has potential benefit to NOAA. And so this is we were kind of perfectly matched here. And so the idea is that the students, you can see kind of on the right, bring new skills to move projects forward, new questions and answers, and get to see a little bit about how NOAA, and in this case, the Weather Service, operates, in addition to things like networking and that sort of stuff too. So part of her cohort from last summer, Candace did a 12 or 13 week stint with us, where some of this work was done, but was also part of her dissertation in a larger project dealing more with machine learning techniques for flooding. So that's kind of the background about how we sort of got here and how Candace and her work was introduced into our office and our office operations. All right, Candace, you're up.
So, as we know, or you might be able to infer, urban flooding, it poses a serious threat to life. And there are instances where people may drown in submerged basements or vehicles. They could become carried away by the waters, and they might endure fatal injuries by the buildings or fallen trees. So the devastation caused by post-tropical storm Ida, that's a recent example of the human endangerment caused by urban flooding. For this incident, there were 91 reported fatalities in the US and 13 lives lost in New York City area alone. So in addition, urban flooding incurs substantial financial strain. There could be damage to structures, train systems, electrical systems, and more. And there are extensive costs associated to repair. So what are the issues encountered in urban flood research? Well, there are warning systems based on the observed heavy rainfall, but oftentimes they don't take into account topography, land surface conditions, or the drainage network. Secondly, many flash flood warnings are sent out on a county scale. So when you're in a city like New York, where there are between 1 to 2 million people in a county, warnings at a finer scale would have greater utility. And then finally, street flooding occurs during a limited time range. So capturing the location and the extent of the street flooding is difficult. It's difficult to obtain physical measurements when the flooding occurs so rapidly due to perhaps intense rainstorms.
Yeah, and in terms of the polygons that we will draw for flash flooding, I mean, we're always looking for ways to shrink those sizes. So no doubt on that. I mean, when you look back at the remnants of Ida, here is the MRMS Q3 48-hour totals here. I mean, no surprise, right? When you're talking the purple and the pinks and the purples here of the 7 to 8+ inches, kind of right through Midtown and into parts of Brooklyn and Queens. And notice the gradient too. I mean, you had a gradient across the city here of like less than 2 inches to obviously much more than that. So this highlighted again and kind of brought to forth the importance of the rainfall rates. Here's LaGuardia's 1 minute precipitation, and you can see in blue is the 1 minute 1 minute values, and then in red is kind of the cumulative as time went on. And so you see basically in this 1 hour period from about 1:20 to about 2:20 UTC. Look at the total rainfall here on the right hand side. I mean, there's where most of the accumulation from that event happened just in a 1 hour period. And looking at some of these 1 minute rates, you're talking tenths of an inch. I mean, that's pretty impressive. So again, this really kind of reinvigorated the discussion about the importance of rainfall rates. I know some of you have probably seen this. This was from our good friends up at the New York State Mesonet. In New York City, we actually are lucky enough to have the Mesonet plus a New York City micronet, which is in part funded through Con Edison, the power company. But just kind of comparing the max rainfall rates between Henri, which was a couple of weeks earlier, to Ida, look at these rainfall rates. I mean, you basically have widespread 2 to 4 inches across the city. And so those are the max values based on the micronet and the New York State Mesonet data through that time. So you can see, quite a big difference from these two systems here. So just kind of to show the comparison. So that, kind of, got us to thinking about, well, based on some of the work that Candace had already done, what if we forced her model with some of these rainfall rates to see what would come out in terms of trouble spots? Are we able to use these rain rates to look to see where we would have trouble? So Candace and I discussed some of this, and she was able to input, and she'll talk more about this, but take a look at what I call the sort of hypothetical 1 inch, 2 inch, 3 inch, and some things in between to look to see what the response is to potential flooding across the city. So that first question really is kind of what we're addressing here. The second question, what if we were able to feed her model with forecast rainfall rates coming out of a CAM, where you would actually have, rather than 1 or 2 inch rates across the city, what if you had model output that showed these spatially varying rainfall rates? What would the response be there? So, just some things that we were thinking about kind of in a post-Ida world, and even before that, really, in terms of taking a look. So really, it's the first question that we're going to kind of look at today. So Candace will talk a little more about the model.
So the issues that we're facing in New York, I know that there's going to be some sensors installed, but at the moment, the issues we're facing in New York is that we don't have quantifiable measurements of the street flooding. We don't know when it's occurring and how. And also, we don't have drainage plans. So the approach was to use crowdsourced data. And fortunately, in New York, there is this platform. It's called the 311 platform, where residents can report street flooding and sewer-related issues. Using New York City as the study area, we also gathered the radar precipitation data, and we've gathered the 311 reports from the New York City 311 reporting platform. And the reports included initially street flooding reports, complaints about sewer backups, manhole overflows, and the catch basin complaints. And this spanned a 10-year period, and it was geocoded to the zip code level. After a few model results and runs, we narrowed it down to catch basin complaints and street flooding only because catch basin complaints had high significance, which we'll talk about in a few slides. But the street flooding complaints, basically people filed them to report flooding or ponding on a street. And then for the catch basin complaints, they file these complaints when they see that the catch basins are blocked or there's a collection of storm water, it's just not going through into the sewer system. And back to the radar rainfall, that was gathered from the National Center for Atmospheric Research, the EOL laboratory, or the EOL website, and that provided 4-kilometer gridded data sets. So from this website, 24-hour radar precipitation data was gathered. For this model that was recently performed for the National Weather Service, only max hourly was taken, but initially we just did the 24-hour radar precipitation data. And then with the Thiessen polygon method, it was aggregated to the zip code resolution. So there were 2 studies that were published that illustrates 2 of the models we came up with. And in one of the studies, the title was Understanding New York City Street Flooding Through 301 Complaints. This was an inference model. It's data-driven. And the explanatory variables were the precipitation amount and the 301 complaints that I was just talking about in the previous slide. We had sewer backups, manhole overflow, catch basin complaints, and then the street flooding was the response. So using and precipitation. So using the stage 4 radar precipitation and the 301 reports over that 10-year period, a lasso regression analysis with a zero inflated component was used to detect the variables that were statistically significant as predictors for street flooding in New York. And the main takeaways or the main results that we found, one was that catch basin complaints, they were selected in 47% of the zip codes as having significance towards street flooding. And then we also noticed that for zip codes that experienced explanatory power from a combined precipitation with sewer backups or manhole overflows, that signified a chaotic condition, perhaps where it's not only raining and the streets are flooded, but the internal drains are also being overwhelmed and they're working in reverse order. And then also we noticed that areas with a high frequency of street flooding reports did not necessarily have the greatest street flooding report increase. And then in these areas, we can see that street flooding might be chronic, and it's possible that the residents are experiencing street flooding during moderate conditions, and that might account for the higher filing of complaints. And lastly, there's that note where the study could have been limited by low resident participation. And we saw this because when we analyzed the increased reports, we saw that there was reduced variability in those areas. And a major takeaway from that is that crowdsourcing does provide insight into the infrastructure. So if we put more efforts to increase resident participation, our model will benefit. Now, the second study was a random forest. So this is a supervised machine learning algorithm. And it was employed to see the significance of the explanatory variables per zip code. So it used static attributes. And that include topographic features, land features, physical and population dynamics, locational features, the infrastructural, the catch basin complaints, and then the climatic influences, which is precipitation. The study also analyzed the socioeconomic variables as predictors. And that was to allow for better insight into potential biases within the reporting platform. And we saw again that catch basin complaints had an overwhelming portion of importance. It had 41% approximately, And the second highest predictor was at 6.73%. So it was dominating overwhelmingly. Now, this could imply that preventative actions such as cleaning the grates will help to remediate the problem. Then we had 141 predictor variables, and when they were analyzed with the street flooding as the response variable, over a third of the top 15 predictors ended up being feature and surface characteristics. And what was especially noteworthy was the building factors. They had a combined 8.72% importance. This is significant because many urban flood studies and models, they tend to neglect the building factors. They'll include aspects such as slope and elevation, but they neglect building factors. And in a city like New York City, where buildings are, or a lot, this is a factor that should be included. We also saw that locational factors were important. The Y coordinate at 4% and the X coordinate at 1%. These were factors relating to the location of a zip code, and it signified that zip codes in particular areas are more likely to experience street flood reporting. And while land feature and topographical conditions may be similar zip codes of the same region, sea level rise may be a causal factor, and that should also be explored. So when we're looking at just the model overview of the negative binomial, we have street flooding complaints and they're discrete. And since these are counts per week, a negative binomial was employed as the link function. This negative binomial model is a generalization of the Poisson regression model. And we have the formula here where Y is the response, and we have the two predictors. So this is for the National Weather Service model, where we're just using catch basin complaints and precipitation. We have decided to just focus on those two since they were the significant predictors in the first study. So we have the formula here, and we have an equation that shows the weekly aggregated street flooding complaints in each zip code. And if you read through it, you can kind of see how the negative binomial performs. All right, so why particularly negative binomial? Well, like as I said, the output values, they were not continuous, they're discrete, they're count variables. So the linear regression model is suitable. The negative binomial was chosen over the Poisson because the mean and the variance are not equal. Also, the NB component accounts for excess variance. I used a few packages to analyze the mean and variance, but R has a count reg package, and it also can analyze the ideal fit for the data when you're thinking between Poisson and negative binomial. So this is just a flow chart of the model we're talking about for today. We have the negative binomial GLM model, and we have our predictors on top. We have the catch basin, clogging complaints, and then we have the precipitation. Our response variable is the street flooding. So with the formula that I had illustrated in 2 slides before, these variables are being input into the negative binomial, and then I'm generating out of sample predictions. 80% was used as training, 20% is used as testing. And then the model was force-fed max hourly precipitation amounts to predict the street flooding complaints based on these hourly precipitation, which we'll show later. And after that, the result is the forecasted street flooding per zip code. So this is exactly what we did. Now for the response, we have the street flooding complaints. it was per zip code, but we also normalized it so it could be per area, per population to account for the space, the general large size of a zip code where street flooding might be more prevalent just because it's bigger. And then also the population where people might report more frequently just due to the size of people. And then the predictors, we have the CB, complaints per zip code, per area, per population. And for our max hourly precipitation, it was taken from the radar, and the Thiessen polygon method was used to aggregate per zip code. And we used a training of 80% and testing of 20%. So the precip values, they're force fed to make these predictions. And we're trying to predict at a max, if there's a max hourly of 1 inch that day, what would our street flooding complaints be? And so forth. So 1.5 max hourly precipitation that day, what would our street flooding? And we went all the way to 3 inch max hourly values. So these are the results when we force fed the negative binomial model. When we were looking at the 1 inch per hour rainfall rates with the max values, you can see that there are certain areas in New York that's having a response. They're having street flooding complaints at this, when there's a day where there's 1 inch hourly rainfall, and that was the max. And we see that in northern Staten Island and eastern Brooklyn, a little lower tip of Manhattan, and then in eastern Queens. Okay, so when we look at 1.5 inch, we notice that there's more complaints now. Staten Island is still concentrated at the northern tip. We have that southern Brooklyn, southwestern Brooklyn. The tip of Manhattan's getting a little more complaints, and Queens is starting to show up. And we know from Ida that Queens is a trouble spot. But we also have the Bronx too. We have South Bronx, and we have the upper eastern tip of Harlem. So now if we're looking at a day where there was a rainfall that had hit 2 inches per hour, we started to see that Queens, that northern eastern tip of Queens is looking as if it has a lot of street flooding complaints. And this also is kind of the area where Ida had a lot of issues. Brooklyn, which is known to have a lot of issues, that southwestern tip, also Staten Island, which is right there, is having issues. So these are areas that's surrounded by water. And we have this the southern tip of Manhattan. And then when we look at 2.5, we see that a lot of areas in New York are starting to experience street flooding issues. Specifically, when you look at this area in the Bronx, right, at the western side of the Bronx, which is also an area that's known to have issues at that highway, that's having more street flooding complaints. Also, Brooklyn and Queens, they seem to be having many major issues. So now when we look at the 3 inch, we see that the majority of New York is having issues. Manhattan seems to be having less issues, and so is the southern part of Staten Island. But the Bronx is having a chaotic situation, Queens especially, and also in that area where Hurricane Ida had fatalities, that area of Queens looks bad. And then Staten Island, the northern tip, and the western, southwestern tip of Brooklyn.
All right, so if we kind of summarize, with the identification of what we call the trouble spots, we basically get these 4 sections. And you can see I highlighted there about the circles, basically northeastern Queens, Jackson Heights to the Bayside area. And again, where those darker shades of green indicate a higher response, a higher predicted response on the complaints. Northern part of Bronx, particularly kind of the east, kind of the southern to northeastern part of the Bronx there. Northern and northwest Brooklyn, and then again part of northern Staten Island. And so those were kind of the trouble spots that came out from the model. Now, interestingly, which is kind of cool here, we actually have a way to sort of independently verify what we're looking at. So if we look back at the last several years of flash flood storm reports from our office, and you overlay those with where the model is tending to predict more of a response based on those rainfall rates. For the most part, you can see the higher density, and I'll kind of toggle back and forth. So these are just the points, and then this is sort of fitting a contour to where the highest density of reports are. And this, I think, is the 2-inch threshold that I selected here. You can see that for the most part, you do have some pretty good overlap, with the exception of Staten Island. And Staten Island always seems to be a bit of a mystery. But you can see that for the most part, those LSRs, or the LSR density, aligns pretty well where you have the greatest response in complaints based on those rainfall rates. If you kind of look at it in a scatter plot sense, I left Staten Island off just because it was hard to fit 5 graphics on here, and the model didn't perform quite as well seemingly down there as it did in the 4 other boroughs. You can see that when you kind of map the LSR count per polygon with the output values, it looks decent up until those higher ends, where maybe not so good. But overall, at least, just kind of from a simplistic validation approach, that looks pretty good. Really what you want to do here is kind of match up the density numbers from the LSR contours to the values coming out of the model. We just have to come back. But that's really what you kind of want to do here, to have a little bit better frequency to frequency matchup for that validation. But simplistically, at least, it looks like not a bad forecast, generally speaking. So integration into our forecast ops, this is relatively new. So we're kind of feeling our way as we go. Our service hydrologist, Nancy Furbush, who I know many of you know, has built this into our new GIS-based hydrology tools. And so the staff is able to look at this in real time to have up almost like an FFPI to utilize during flash flood events. Now, interestingly, and Candace mentioned this earlier, this is kind of our supplemental, what I call the supplemental data resource, the data that we have from other sources that are utilized as part of the forecast and warning process. And Candace mentioned these observations in and around the city that are starting to pop up through a joint effort. This is in a post-IDA world that is actually looking at monitoring street level water depth. And so they're going to be deploying 500 of these sensors over the next 5 years that basically hang down from street signs and are pointed downward, looking at water depth at that street location. And so, some of this information coupled with these new observations kind of are going to allow us, hopefully, to get a better read of what's happening on the ground in real time. And these are, I think, like every 5 seconds is when this information comes. And we have a couple of sites now located basically in Brooklyn, Southern Queens, and then maybe 1 or 2 up in the Bronx. But again, when the city is peppered with 500 of them, will give us an additional eyes on the ground, boots on the ground view of what's happening. So again, some of this work, is considered what I consider the supplemental data set, and can be used sort of as a flash flood confidence, knowing that is a booster, right, for warning issuance, in the sense that we know that we are expecting impacts of some sort, and when we start to get those rainfall rates, kind of maybe will allow us to make some decisions on where to draw our polygons. It also gives us some spatial context for DSS, and that, kind of looking out in the forecast realm versus the warning realm, will give us some ability to do that. So kind of in the DSS realm, before the event, able to match up some forecasted impacts based on the rainfall rates that we may be expecting or maybe forecasting. So that brings up the question, transferability. We haven't used this yet. We haven't had the chance in a real flash flood event to have this up and used. We'll hopefully get some, hopefully or not hopefully, I suppose, get some at-bats with it here this spring. So, bottom line here, As it turns out, this mouse wheel is very sensitive. All right. So we haven't been able to utilize this in real time, and the transferability of this, so is sort of an interesting question. You know, we always want to, when we start on these R2O projects, you want to make sure that what you're doing could actually be used somewhere else. And in this case, the technique and the methods are certainly transferable to other urban areas. The issue, of course, is like with all things, you know, machine learned or artificial intelligence related, it's the input data that's the most important. And so, you know, based on the fact that we have, you know, the initial training of this model was done utilizing this very specialized New York City 311 plus other New York City centric data sets would be a challenge. But so you'd need some addition, you know, you'd need the high resolution data similar to what the city has to basically train the model. So the transferability at this point, I think, is somewhat limited, although the technique and the methods, generally speaking, certainly would be. Candace, I'll let you do this part.
So, so a few of the forward directions that are possible, we could dynamically source eyewitness accounts, where we could use a combination of databases that could accompany the New York City 301 reports. For example, we could use localized news reports. Social media is also an ideal crowdsourcing tool. Specifically, Twitter provides a developer platform, which could be used in conjunction with Google Maps API to aggregate and map tweets relating to flooding. And in the last stages of my research, I was developing this type of platform where I was implementing Twitter to map keywords that were related to street flooding in New York. And then when I'm looking at this chart on the right, we see that in the last decade, there had been an increase in machine learning methods. And it seems when you look at that green line, that is showing that artificial neural networks have the highest number of articles, but decision trees like the random forest is also pretty high. And then we also see that support vector machines are increasing, but overall machine learning tends to be increasing. And right now I'm using a graph neural network to predict stream flow for river basins, but there's this another type of deep learning where there's a graph neural network and it combines with a wave net. And the nice thing about this model is that it can incorporate static attributes and also time series. So the random forest had worked with the static attributes, and then the negative binomial was working with time series, but this model can incorporate them both. So I believe that that's going to be the next step in my research once I finish the river basins, is that to put this model into street flooding use.
Yeah, the other piece of this too, in kind of thinking about some of the output here and some of the you know, thinking about social vulnerability, again, keeping in mind that some of this SVI information is included in the initial conditioning of the data. You know, do we have an opportunity here to improve our call to actions for flash flood warnings? You know, if you kind of overlay, you look at the picture to the right, this is the overall 2018 SVI for the city, with those darker, you know, that includes language, economics, those sorts of things. You sort of overlay, you know, the areas where many of the complaints, at least based on the model are, and again, I think this is for the 2-inch mark, you see some pretty good overlay there. So obviously in the, you know, very confined space that we have here, you know, certainly some opportunities along this realm. Our office is part of a project with the Office of Dissemination at headquarters looking at multi-language warning output. So can we utilize some of what we're learning here in terms of locations to actually improve our messaging in different languages? So that's another thing that's sort of in the back of our mind here as well. And then, of course, you know, again, looking ahead in terms of, you know, before the warning process, what we're, you know, what's sort of been given to us as this hyper-local, you know, sounds very media-like and newsy, but, you know, folks are looking for more and more detailed, almost like site-specific information for this. So do we have some opportunities ahead of these events to maybe provide some additional detailed targeted DSS to some of these locations, and more to the point, some of the communities that reside in some of these trouble spots. That's the summary here. That's it. No silver bullet. And again, those of you that live in urban offices, I think, that live this know it. And some summaries there in terms of kind of what we found and how we are going to utilize the output of the work, for the upcoming flash flood season, and the integration into our hydro viewer, and kind of utilizing this in warning operations as a confidence nudger, but also kind of pre-warning in the IDSS realm, or even in that period, that the gap there between watch to warning time frame. Is there some additional information, via social media outlets or whatever, in terms of the DSS that we can do. So that's the plan going forward. And I think with that, we talked for about 45 minutes. I think at this point we can take questions or discussion. Jordan, I'll turn it back to you for that piece.
All right. Thank you, Dave. And especially thank you so much, Candace, for all this great research that you've done. And really also, it really highlights also the value of the NOAA Near To program as well. So we must not say that as well. This is really great information shared this morning. Both, I think of it from a situational awareness standpoint of what the information from this model can glean to operational considerations in flash flood events, and especially ahead of flash flood events, to be aware of these details. And I think also another aspect would be, Dave, and you mentioned this too, the prospect of having opportunities to implement this in operations moving forward, and potential opportunities to also share this information as well with other offices along I-95 and the interior that have respective urban centers as well. So I think there's a lot of potential. And I think part of that will also depend upon the opportunities that arise moving forward to test this, not just in a retrospective context, as was shown today in the context of IDA and the other events that you shared this morning. I had a question, but I wanted to first open it to the floor if anyone had questions or thoughts from the field virtually this morning. Yeah, it's not. Go ahead.
Yeah, this is great stuff. I am really excited about trying that same approach in some of our urban areas. I know that a lot of the combined sewer areas in the Midwest have, as part of their consent decree, had to put in systems like that 311 system to give residents a chance to talk about their, impacted basement flooding. Mostly in our area, it's basement flooding. And then I think about that along with what we're seeing in some of the work that's being done at the National Water Center in terms of putting together flood inundation mapping, where in urban areas, there is no delineated stream. So you have a big gap where the people live, that we're not going to have flood inundation mapping in urban areas because there's no streams. And so tools like this fit much better with the need for the type of, kind of warnings that you have to put out in terms of, high intensity rainfalls and what's going to happen with them. So I'm really excited. This is fitting in really well with sort of a gap that I see in the way that the Water Center is putting together their flood inundation mapping for urban areas. So this is cool.
Yeah, thanks, Trent. There's a group out at Stevens Institute that I believe is working with the water model developers to try to bring an urban component to the water model. That's about all I know, and I'm sure that it's not going to happen overnight. So we're cautiously optimistic about the longer term piece of that, with utilizing some national water model data to help us under this. But thank you.
So my question was actually just covered. I was going to ask, Jeff, go ahead.
Okay. Candace, I was wondering, in your working with the crowdsourced 311 data, I'd imagine in a coastal city like New York, there is a small subset of these problems that maybe could be due to more of a seawater storm surge, water backing up, or either being the causative or an exacerbating component. Was there any attempt to kind of filter out those, maybe those causative events from the ones that were more purely associated with heavy rainfall rates?
Yeah, that's true. Sea level rise, it is a factor in urban flooding, and some of the areas might be having a combined experience of flooding due to the drainage system, and then also flooding just due to the waters coming across into the streets, such as East River. The east side of Manhattan tends to have that water coming from East River. The one thing that's, and I think that's a really good future direction, is to also incorporate this type of sea level rise and see the exact contribution it has towards certain areas, especially in Brooklyn and on the eastern side of Manhattan. The one thing that's interesting, though, is the catch basin complaints. It signifies that there are urban details that are influencing this type of flooding. And when you see certain subway systems that are flooded, or even in Queens during Ida, these areas, they're not particularly at the coast, but so it's a combination of factors, I believe, that cause flooding in certain areas.
One of the really kind of neat things we'll be able to see, I think, from the New York City FloodNet, we've been encouraging them to not forget about the coastal spots. There's been a push to try to put these sensors in the interior, and again, kind of as a result of Ida. But there's a coastal piece of this, I think, or near coast piece of this that I think will be just as interesting. So you can imagine watching, in a case where you have heavy rainfall plus coastal flooding, to be able to see the response in basically 5-second intervals will be pretty cool. And that's information that we really obviously haven't had access to even understand the response for those combinations. So I think that's one of the things that this new network is going to help us to understand the science behind it, or the response behind it, I guess.
Thanks.
Thanks, Jeff. Any other questions from the field or thoughts, reflections? Okay. The other question I was going to ask was already actually addressed 1.5 times. No, all I'll say is this is really excellent work. It's just really good to see the visualization of the issues, of the dilemmas and the problems that are dealt with in an operational context, and being able to represent that in graphical context is everything over just discussing it and seeing it in a text form. So seeing it visually is everything. So is there no other questions? The only thing I was going to suggest for moving forward is this would be a great opportunity to also do future sharing of this, pending the results, this coming season. Again, hopefully we don't have flooding events. I know it's a reverse psychology thought, but perhaps we have a low end one to test it a little bit, and take it forward from there and share it accordingly with other urban centers around the region. And, there's always the no one size fits all, but it sounds, by the dynamic nature of this model and the things it takes in, could be versatile in other zones as well, specifically to other WFO, CWAs, and RSAs. Jim.
Hey, Jordan and Dave, thanks for the presentation. Great job. Candace, you too. Can you share these slides with us? Would you mind?
Yeah, we can get the slides uploaded along with the recording to the Eastern Region SSD sign sharing Google site page. And we'll share a mention when that's completed as well. So we'll do. Any other thoughts or questions this morning? I don't want to stop a meaningful conversation, but I guess May you explained it really well. So I guess again, I'll say, Candace, thank you so much for all the work you've done with the OKX staff and specifically Dave Radell too, for helping to facilitate this work over the last year plus. And I guess with that, we'll wrap up a few minutes early before the top of the hour, give someone some time back. So thank you again so much for everyone attending this morning. And yeah, we'll speak to everyone again soon with upcoming webinars. That's all for now. Thank you so much.
Thanks for having me. Thanks for having me.